Now, all our lives are governed to a large degree today by electricity. Now, almost everybody has experience of getting a shock, I'm assuming, right? So, whenever you put your finger into a plug and you don't want to do it again, probably you would have got a nice shock. So, what went through? Current. Okay. So, the study of current, the study of flowing charges, the study of lights, fans, AC, bulb, almost everything, cell phone, satellite, everything today is run on electricity, and the study basically is called circuit theory. We are going to study electric circuits and current electricity in great depth. Okay, and the first question is, what makes all these things run? Why does the fan go around? Why does the bulb light up? So if you look at the bulb, now current enters the bulb. Basically, current is a set of charges that are flowing in. The charge comes in and the charge goes out. The charge doesn't stay in the bulb, but the bulb basically lights up and so sends out energy, right? So what can you conclude? You can say that the charges came in with energy, gave that energy to the bulb and went out with less energy. What gave energy to the charge? That's an important question. Okay, what makes this charge go around? That's also an important question, right? What makes all of these things work is one single idea, and that idea is called electric potential. You might have heard of the word voltage. Voltage is nothing but potential drop or potential difference, right? So if you look at electric potential, everything actually runs on this one single idea. If you understand this, pretty much everything we should be able to understand a lot better, because ultimately, why does the charge get energy comes out of this. Why is the charge running around comes out of this. Now, what exactly is electric potential? We won't answer that right now. In fact, we won't answer that for a long time. We will come back to electric potential in great detail when we study electrostatics. What is important, on the other hand, for us right now is to understand that every point all around you, every point in the universe, every point on earth, just the point above my head, the point on the board, this point, that point, just above you, okay, your nose, every single point has a number, an electrical number. That number is called potential. Okay, so let us take the example of this point and say, let's call this A. This point may have a potential, let's call it 11. This number is 11. Now we have units for this number. One of the guys who spent a lot of time studying this, his name was Volta, and so in his honor we call this volts. So we'll use the symbol V. So we say 11 volts. So this point's number is 11 volts. And if I look at this point, let's call this B. This point may have some other number. Now maybe it is 15.6 volts. Now you may think, okay, all of these have to be positive numbers. No, maybe this point has minus 5.8 volts. This point may have, let's call that D, minus 16.3 volts. The key idea is every point has a unique number, one number. So this cannot have two numbers. One number, one number, one number. So what is the first idea? One might like to think that, oh, so A has 11, so no other point has 11. No, that is not correct. This point E could have 11 volts. Okay, what did I say? I said every point has one number. I didn't say 2 points can't have the same number. Right now I am wearing one t-shirt of one color. I am obviously not wearing two t-shirts. Does that mean nobody else can wear this red t-shirt? Of course they can, right? So the basic point is two people can have, or 2 points can have the same number, but 1 point cannot have two numbers or 3 numbers or 4 numbers. If this is 11 volts, finished, right? You can't say this can have 11 volts and 13.7 volts. Not possible. But that is not completely correct. Okay, and I'll come to that in a minute. What I want you to understand is, what is this number is not something I'm telling you right now. How did this number get calculated? How do we know it is 11? I don't know. I'm just telling you this is 11, this is 15.6. Every point, here there is a number, there is a number, and it's real. Everywhere there is a number. Okay, I'm not just trying to make this up. Now the key idea is, if I go and switch off the light, suddenly all the numbers everywhere change. So this 11 might have become 5. But you don't have 11 and 5. You have 11 or 5. This thing may go and it may become -6. Now, it's not that if it was positive, it will remain positive. This could go away and this could become -3.8. And this could become -16.9. Okay, and this may not change at all. We don't know. So, every time I switch on a bulb, walk around. I am a conducting object. So, if I walk around, all these numbers might change. Okay. If I bring a battery nearby, numbers will change. If I bring a charge nearby, numbers will change. Okay. But at any given time, at one time, you say at 1 o'clock today, this has 5 volts, that has -3.8 volts, and so on. At that time, this cannot have 5 and 8. But at 2 o'clock, this might have 11 volts because somebody came, switched on something. Okay, current somewhere, power got switched off, something happened, all the numbers changed. But at any given time, every point has one unique number, and that number is what we call electric potential. Okay, now later we will learn, right now it's a little too much to start with, but if I come and take a positive charge and I place it there, that positive charge, let us say, has a charge of value something, 2 coulombs. So this is charge of 2 coulombs. If I bring it and place it at A, then 2 times 5, because its potential is 5, it has an energy of 2 times 5. So think of it that way. We'll make this much more better when we study electrostatics. So Q times V, if I call V potential, the energy when the charge is at A is Q times V of A, the potential at A. Usually we use the symbol V at A to say potential at A. So what will be the potential at C? V at C. Okay. So this charge, if I take this charge and move it there, how much energy will it have? Charge times this potential. So now it will have actually negative, if it's a positive charge times negative potential, so it will have negative energy. Okay. So the energy of the charge depends on the potential. Okay, and that is one of the reasons that charges run around in a loop, and this loop is what we call a circuit. So let us look at a simple analogy. Okay, something that will connect us to potential, because potential is an abstract idea. So when I tell you there is a number here, you can't see the number. In fact, you may not even be able to see the point. But every point has a height, right? This point has a height from the floor or from the sea level. What about that point? Can this point have 2 heights? No. From the floor, this has 1 height. So in fact, if I say this is the floor, we usually call that the sea level or the ground level or zero level, whatever. Now imagine that I am going like that. Now is it possible that there are 2 points with the same height? There are many points with the same height. This point has the same height as that. This has the same height as that. In fact, in air, this point has the same height as that. Suppose I say this is 4 meters. This is 4 meters, 4 meters, 4 meters. Which means the height of this point is 4 meters. There are many points with 4 meters. But if I ask you this point, how many heights does it have? 1 height. How can a point have 2 heights? In many ways, isn't it like potential? Now one might think, wait. What if I look at this point, but I want to measure the height from here? I might get a height of 2, right? So this point can have 2 heights, 4 meters and 2 meters, right? Yes, it can. It can. But actually, usually when we talk about measurement, we first fix a reference point. Once this point has been fixed as 0, now this point is not 0. From 0, this has a height of only 4 meters. If I made that 0, what is this point? This will become -2 meters. Okay, so you have to set what we call the 0 level. Once you set the 0 level, from the 0 level, everything else is fixed. Now, if I decide, no, I want to make everything, I don't want to measure it from here, I want to measure it from here. And let's say this was 3 meters below, that is -3. Okay, now 0 itself has become +3. This is now my new 0. If I make this the new 0, this has become 3. That would have become 3 plus 2, 5. And that will become 3 plus 4, 7. So 4 will become 7 meters. But then this 4 will also become 7 meters. This will also become 7 meters. right? Everything will become 7 meters. So actually what we need to understand is you're setting a zero level. The same way actually for potential also, if I had multiple points, if I said this was 4 volts, A has 4 volts, let's say this was B which has 6 volts, and let's say this has minus 3 volts C, and this has 8 volts, and let's call that D. This is all assuming that some point is called as 0. Now can you have multiple places called 0? Yes, because this is 0, this is 0, this is 0, this is 0. Or this is 0, this is 0, this is 0, this is 0. You can have multiple zeros, but wherever you decide to call 0, so suppose I said this is 0, then that is 4, then that is 6, then that is minus 3. Suppose I say no, I don't like this to be 0, I want to make this 30. I've added a 30 to this fellow, okay, which was the original 0. Now what is going to happen is everything will increase by 30. So this will become 34, this will become 36, this will become 30 minus 3 or 27 volts, and this will become 30 plus 8, 38 volts. So the number is dependent on where you decide or what you decide is the 0 level. But the main point is, I have not even told you how to calculate it. But if this is 34 and that is 36, it is 34. You cannot at this point have two numbers for it. And that is the key idea I want you to keep in mind. Okay? Every point has a number. The number could have changed. The calculation of the number can change when you change the 0 level. But once I set a 0 level and start calculating, just like heights get fixed, this number also gets fixed. This point can have 11 volts. That's it. It cannot have 12, 13, 14. But can 2-3 points have 11 volts? Yes. So in many ways, this is the same idea as height. And you will see that there is a lot of connection. Remember I told you that the energy of a charge when it is sitting here, what is the energy of the charge? Charge times potential, right? So charge times potential is the energy. Correct? Now, if I look at this height, if I come and bring a mass m and I keep it here, if I bring some mass and let's say that mass is sitting there, mass m at this height h. Okay. Now mass can be converted into weight. How much? mg. So instead of doing that, if I write the potential here, gravitational potential, I can think of it as gh. Okay, so what will be the potential energy? Potential energy is mgh. This should be called electric energy, should be called QV. So can you see that charge times V and weight times h, or actually I will usually what we will do is we will take GH. So we will say mass times height. GH is just a factor. So the basic idea is just like an object has, what does it have? It has potential energy at this height. And if I move it here, what kind of potential energy does it have? Lesser or more? Lesser. And if I move it up? More. And if I move it like this, it will have the same potential energy. So if I moved it like this, so from this point to that point, it has higher potential energy, right? So at each point it has a different potential energy, and the potential energy depends on the height. Same way, at each point, a charge has different energies, and the energy depends not on the height. Right now I have made it look like 11 volts is above and 8 volts is below, but what I am going to do is I will come here and I will show you that this is 15 volts. Because you don't have, this is not related to height. I am telling you it is like height. I am not saying it is height. It doesn't mean higher points have more potential, lower points have less potential. Okay, this is an electrical number, it has nothing to do with height. For gravity, height matters. For electricity, electric potential matters. It is like height in the sense that height, the potential will tell you what is the amount of energy. But there are differences clearly because you have, all masses are positive. But charges can be positive and negative. So if I had a negative charge sitting here, I will have negative energy. Okay, if I have positive charge, I will have positive energy. But if the potential itself is negative, of course you will have negative energy again for a positive charge. Okay, so the basic idea I hope is clear. At each point you have different potential, and at each point you also have different amounts of energy. The charge has different amounts of energy. The energy of the charge depends on where it is. Same charge. Suppose I had a charge which was 2 coulomb. So let us say Q was 2 coulomb charge. If I kept the 2 coulomb here, how much energy will it have? 2 times 11, 22 joules of energy. But if I bought the 2 coulombs from there till this point, 16 joules. And if I bought the 2 coulombs to this place, 30 joules. Because you're going to say 2 times 15, 2 times 8 and 2 times 11. Now, something very simple and interesting that we do know is if I let this pen from here, what is it going to do?
It's going to drop.
It comes down. So can I say that this pen that I dropped from there reaches this place and then falls down? It had a higher potential energy and it has a lower potential energy. So the pen moves in the direction of reducing or lowering its potential energy. We can say that. We can also argue that this is because there is a force downwards, but generally if the potential energy is reducing, objects try to do that. We like to lose energy. Now we may not like to, we don't probably believe it, but we like to lose energy. We all think we want energy. We want to gain energy, right? That's not true. Why do you want to gain energy? Do you like to earn money or do you like to spend money? Which is more fun?
Spend money.
Spend money. But you like to get the money. Why do you like the money? So that you can spend it, right? So actually we want energy so that we can spend it, because spending energy is more fun. Objects like to lose energy. Now this fellow is not going to say, let me go grab energy and collect it. But if I have energy, what is it trying to do? It's basically trying to lose it. Now the same thing is true not just for us or for the pen. It is true for every kind of object. All objects try to lose energy and go to the lowest energy state. Now you see, if I keep the 2 positive charge here, its energy is 22 joules. If I keep 3 coulomb charge, it will become 33 joules. But right now I want to take the positive charge. So how much energy does it have? 22 joules. If I take that positive charge and keep it here, how much energy will it have? 16 joules, because 2 times 8, 16 joules. Which is less? 16 is less. So if I manage to connect this fellow to that fellow and the charge can somehow flow, the charge will flow. It will go from here to there. Positive charges will go from higher potential energy to lower potential energy, because everything likes to go from higher potential energy to lower potential energy. And what is interesting is, if I keep the same 2 coulomb charge here, it will try to go from here to there. It's not going up. This is just down, up physically. But remember, energy depends on electrical number, not height. Height is true for potential energy physically. This is an electrical number. So this fellow, if I leave the positive charge here, it will try to go from this point, because here how much energy does it have? 30 joules. I told you it is Q times V, so 2 times 15, 30 joules. So if I leave it here, it will try to run there, because that is 16 joules. If I connect this to this, what will happen? This is 30, that is 22, so it will go from 30 to 22, it will go like that. The charge tries to lose energy. But instead of a plus charge, suppose I had minus 2 coulombs, this will become minus 22, minus 16 and minus 30. So this negative charge will go that way, negative charge there will try to go this way, and negative charge will go that way. Now we don't have negative mass. Maybe if we had negative mass, you left the negative mass here, it will jump up. But we don't have negative mass, so I can't show you. But we do have negative charges. In fact, most of the time we'll be dealing with negative charges. Electrons are negative charges. Okay, but I hope the basic idea is clear. So can you see that this number and that number is the reason charges move? Because these numbers tell you the energy, and it's trying to lower energy. Therefore, it's trying to basically go from, if it's a positive charge, it goes from a higher potential to a lower potential, and it loses energy. How much energy? Well, it lost from 11 to 8. What was the loss? 3. It lost 3 volts into 2. Because the energy it lost was 6 joules. But forget the Q. The drop in potential is the driving force for a positive charge. Is that clear? Now that means something very interesting, because what we are mostly interested in is if I start here and I go there, let's say that was B. Okay, I'm redoing this. Let us say this was 11 volts and that was 8 volts and this is C, and let's say this was 15 volts, right? This is what we started with. It could have been negative, positive, doesn't matter. From A to B, if I look at how much is the drop, what is drop? Generally in physics and in mathematics, we talk about increase, rise. Rise is final minus initial, except for electric circuits. Here we are going to talk about potential drop. Okay, what is potential drop? From the initial to the final. So therefore the drop, we usually call this potential drop from A to B, VAB. What is this? VA. What is this? VB. VAB is VA minus VB. And that is equal to 11 minus 8, 3 volts. Okay. Now if I go from A to C, what should I call this drop? VAC. A to C. And it is always VA minus VC. Okay. I am going to use consistently potential drop. In books you will see potential difference, you will see voltage drop, you will see lots of different words. They all basically mean potential drop. Sometimes people use potential difference to say potential rise. That makes things a lot more confusing. So I will suggest that you focus on potential drop as the key term to use. And it's very clear when you're talking about drop, it is initial minus final. Okay, so VAC, how much is that?
11 minus.
So this is 11 minus 15. So what do we get? Minus 4 volts. Now can you see that potential drop can be negative, potential drop can be positive. Okay, and what about the drop from B to C?
Minus 7.
8, 15. So what should I call this? Potential drop from B to C. Now going from B to C is 8 minus 15. Okay, VB minus VC, because initial minus final. It is the opposite of final minus initial, which is what we have been doing. Whenever you use the symbol delta, remember it is usually final minus initial. So suppose I say delta X, it is X final minus X initial. This is not that. This is
Initial minus final.
initial minus final. So I shouldn't be saying delta V, I should be saying minus delta V. Okay, but generally we'll call it potential drop. That's why the symbol VAC, VBC. What is this? Minus 7 volts. Something interesting. What is this drop? 3 volts. What is this drop? Minus 7 volts. What about 3 and minus 7? Minus 4 volts. And what is this drop? Minus 4 volts. We'll come to this in a minute. Okay, we'll soon see it after a little practice. But what I want you to understand is VAC versus VCA. What if I go from C to A? So if I do VCA, it is VC minus VA, which is how much? 15 minus 11, and that is 4 volts. So can you see that VCA and VAC are opposites? But that makes sense, no? If I fall from here to there, I have fallen by 4 meters. If I have gone from here to there, I have risen up by 4 meters. How much have I fallen by? Minus 4 meters. So if this is plus 4, this we usually call minus 4 in terms of falling. Distance is the same, but the fall is a direction, no? The same way we are going to talk about potential drop from A to B. Well, the drop from A to B is 3 volts. The drop from B to A is minus 3 volts. Is that clear? So let us just apply this idea to a few problems, and then we will see that this idea itself is a very powerful principle. A German scientist called Kirchhoff did a lot of work on this. Such a simple idea, saying that this drop plus this drop is equal to that drop is one of the foundations for the whole of electricity. You may not believe that, how can this such a simple thing be such a big foundation? But it is. And the idea that we started out with, saying every point has a unique number, is the same as this statement. Okay? Okay, so now we know how to calculate potential drop, right? So if I start here and I end there, you know how to find the potential drop from A to B. We have seen that it is VAB, which is VA minus VB, right? That's what we saw. So this tells us something about how to do this calculation. Now I can go further and I can go from B to C. And if I did that, this would be VB minus VC, which is VBC. I can call this entire thing VA to B, B to C as VABC, and that turns out to be VAB plus VBC. So VAB plus VBC. Okay, but it is also interesting that VAB plus VBC is VA minus VB plus, because that is a drop, plus VB minus VC. And if you notice something interesting, the VB, VB will cancel. And so what is this? VA minus VC. VA minus VC is VAC. So whether I call it VABC or I call it VAC, it is the same idea. We will spend a little bit more time. Once you get some practice with some of these calculations, we will see. So calculating potential drops is a very important idea, because that's what allows us to calculate the flow of charges, allows us to calculate how much energy a charge is going to lose or gain when it is traveling, right? So those are things that are, in fact, this potential drop is what drives charges, and that's what we started out with, right? Now you may be thinking, all this is fine, you're telling me to calculate potential drop, you're telling me to do some addition, all that is fine, but what exactly is this potential at A? I know it is 11 volts, fine, but what is this 11 volts? How do we know it is 11 volts? We have not answered that question. We will answer that question later when we study electrostatics. Okay, this thing is actually created by charges. So how do we calculate this? Well, if you have a charge somewhere, that produces a potential there. And I already told you that if I change the zero level, this number will change. So this number is a weird kind of number. Right now, don't focus too much on what exactly it is. Let us learn how to use it. Assume that every point has a number, and let's play around with it and see whether how far it takes us, where does it lead us to.